All right, you just took your quiz. I haven't made one of these videos in a long time. Let's see if I can remember how to do this. All right, this is just a warm up. What exponent do we put on 3 to make it 27? What exponent do we put on 6 to make it 1? Etc. Bam! Okay, so most of those are pretty easy. You should know those. A couple interesting ones. What's this supposed to be? Well, if we're talking about a log with a negative number in here, that's not supposed to happen. So, yeah, that's kind of a problem. The other one that's kind of interesting is this one down here. Now, this thing at the top says no calculators. How in the heck are we supposed to do this with no calculator? I did this on the calculator, and yeah, it's not a nice number. So this would be a calculator problem. I would say let's do it that way, and the answer I got was 3 point. Oh, if it's going to be 3 decimals, 3.907. Okay, we'll say approximately equal to 3.907. Okay. All right, so this is just a reminder about the definition of logs and all that kind of stuff. And yeah, here it tells you that y has to be positive, right? That only works if y is positive. Doesn't really make sense if b is 1 because, 1 to any power isn't going to go anywhere. And also b has to be a positive number. Okay, and we did this last time, so this is just kind of a review, so I'll just do that really quick. Remember that this is just the inverse of 2 to the x power. So if I wanted to say 2 to the 0th power, that's 1. 2 to the first power, that's 2. 2 to the second power, that's 4. But I'm kind of doing this backwards, right? The x's and the y's. And this is where I get the half and the quarter. And if I graph it, I put points on kind of like that, and it looks like, this would be really hard to do with the video equipment, but oh, hey, that's not bad. It's going to look like that. It's the shape, it's the same shape as the logarithmic function, but it's the inverse, so it kind of goes this way. The asymptote is a vertical line on these, remember, because y is limited by, x is, the number that goes in here, which is actually the x on this one. X has to be greater than 0, so the asymptote is that vertical line at 0. That also means the range is where x is positive. The domain, though, it can be any number, real number. This can turn out to be anything. The x-intercept, where does this cross the x-intercept? It crosses at 1. You could also call that a little more responsible to specify it's when y is 0. But when x is 0, this doesn't exist. So there is no such thing. That never crosses the y-axis. Okay, again, that was kind of review. What if we compare a bunch of these at once? We could say, like this red thing here is y to the 2x. The inverse of that is the logarithm function. It looks like this. If we were to raise the base a bit, so this might be like y to the y equals 3 to the x. We look at this blue one, maybe y equals 4 to the x is this, I don't know if that's what this actually is. Let's say maybe this is 3 to the x and then 4 to the x. It would look kind of like this. This would look like the bases of those over here. The log base 3x would be kind of that one, and the log base 4x would be this last one over here. On Desmos, this is pretty cool. Oh, wait, wrong video. On Desmos, let me move this over so you can see it. Sorry, this is a little bit of a mess. I graphed this, so you can see what I graphed. I graphed log base n of x, and I made a slider for n. So if you move the slider, can I get this in one? You can kind of see it if I do that, I guess. You can see what I'm going to, I know, I can move this over. All right, so if n is the base, so if n is 2, it's kind of like that. If n is 3, it looks kind of more severe. If n is 4, it looks even more severe. If n gets really far down here, like if n gets to 1, it gets really weird. Like we don't let n equal 1 because that would just kind of go away right at 1. If we let n be a number less than 1, it's going to look like this. Think about why. And you can actually let this play, and it kind of does this. This is kind of cool. So notice on all of these, the asymptote is going to still be the x equals 0 line, the y-axis. It seems like it's kind of pinned down right here all the time, no matter what n is, at 1, 0. So that means if we put 1 into this function, the log, no matter what the base is, log of 1 is going to be 0 because anything to the 0th power is 1. Okay, that's kind of mesmerizing. You can watch this over and over again. That's kind of fun. Okay, yay, Desmos. You can actually put in sliders like that on your calculator too. It's not as fun to watch that animated. And guess what? Here's the notes where they put this stuff in. It was all over the last homework. You had this, like I kind of added to the end of the last notes. But let's just redo this here. Okay, log of a product is, we're going to keep the same base. But you can separate those out, and that's log base b, so I don't know what that little dot oh, I need to write an m, thank you, plus log base b of n. If you have this division, it's the same kind of idea as we had with exponents. Keep the same log base b, but this is m minus all that stuff. And I bet you're thinking, wow, this has been great before the quiz. This one, if it's on top, outside, you can put it out here, out front. This is c times the whole thing. And change of base rule. This is actually maybe the most interesting one. You actually use this a lot all the time, especially if your calculator has limited functionality. Anyway, I'll show you what I mean is if you knew one of these bases was easier to contribute than another one, or you just had some other base you really like to use better, or for whatever reason you want to change bases, you could invent a new base here. Log base a of m divided by log base a. This is what we're calling change of base. We're adding in a new base that's also an a of b. So I could take this m and this b and kind of make a new fraction where I have log m over log b. That base could be 10, so you could really just write it as log m over log b, and that would equal this whole thing right here. That I don't think was on the quiz, so there we go. Expand the following expressions using the property of logs for its simplest terms. Okay, so if this x wouldn't have been here, this would have looked more like a quiz question, right? Like it would have been okay to have log 3, 9 and deal with that. Well, we can use that and still deal with that, and that's easy. We can separate this out as a sum. So that's going to be log base 3 of 9. Now it's just 2. Whoops, I said 2. That's going to be 2 plus log base 3 of x. I don't really think there's anything we can really do to that. That's the exponent we put on 3 to get x. So that can't be simplified any further. But the 2 is kind of nice, and maybe that looks better than this. This one is the subtraction one. So log is base 10, 3y minus log 7. I can kind of split this up a little bit and call this log 3 plus log y minus log 7. Those are all simpler than this thing. Log base 6. Okay, and then this is going to be a big subtraction in the first place. Log base 6, 6x cubed minus log base 6 y, and then of course this thing I can separate that out as a sum. Log 6 plus log 6 x cubed minus log 6 y. Wow, this is a lot to write. Log 6, that's easy, right? 6 to what power is 6? That's great. 6 to what power is x cubed? I don't know, but that exponent on top, I can write that out front. That's 3 times log 6x. And then this I can't really simplify anymore. So we're just kind of busting these up as much as we possibly can. Kind of applying all the rules that you can apply them. Just going to show off all your rules. All right, log 100 minus log, oh, can I just do this all at once? Log x squared plus log y. Save me some space, and then we're good at that. What's log 100? Well, that's the exponent you put on 10 to get 100, so that's 2 minus this 2 I can put out front, 2 log x, and I think I'm kind of done. Can't really combine that any better. Okay, compress the following expressions using property of logs. Okay, so by compress they mean can we write this kind of any smaller than what we've got here? Again, I think given the instructions and given the rules you have on logs, just try whatever rules you have and see what happens. Like this is going to be, this is a subtraction and it's the same base. I can read, like basically we're just going to do this backwards. This is log base 5 of the division, which feels a little bit different. We don't really do that. You know, we're kind of used to busting these up the other way. This is kind of collect it back together. And what's kind of nice about that is 8/12 reduces to 2/3, right? Can't really reduce that more than that. This is a sum, so I would go, oh, first of all, this is the same thing as log x squared for one thing. But this is a sum, so I would take that basically times 5. It's probably easier to write that as log 5x squared. And let's assume that that's all inside the log function. Okay, same kind of instructions. Log 316, I can't really do that by myself, like 3 to what power 16. If that was maybe 2 or 4, I could do something about it, but 316, I kind of got to leave it. These are all base 3, which is a huge bonus. This is 16, and this is x. Oh, you know what? First of all, this is going to mean, save some space here. There's this half out front. It's the same as having a half on the exponent out here, which is the same as the square root of x. This is a plus, this is a minus, so we're going to add these first and divide by that. So this is going to be log base 3 of, adding this means we're doing 16 square root of x. Oh, I should probably make this a little bit raised because I'm going to divide by the 4 down here. 16 squared of x. Yeah. Oh, and I can reduce that a little bit, right? Because 16 over 4 reduces log base 3 of 4 times the square root of x. Interesting. Oh yeah, because 16 divided by 4, I could have put this over here in the first place and then 16 divided by 4 and just had a 4. That was kind of silly. Okay. Log 15 minus log 5. This is all base 10. This is like saying log, if you think about 15 divided by 5, this is really all like saying 3 here, which may surprise you. Half log 1/25th, this is like 1/25th to the 1/2 power. What's 1/25th to the 1/2 power? Oh, that's this, that's 1/5. Log of 1/5. And these are all base 10. This is like saying 3 squared. I can multiply these. This is like saying log of 9 times 1/5. I'll just say 9/5. Okay, almost done here. Evaluate following expressions. Use the properties of logs as necessary. No decimals, so this is supposed to be kind of like a no calculator skill for the most part. A lot of these are quite easy. I'll do those first. All right, the first few of these are pretty easy, so I'll just stop at the first one that stumped me. Actually, I can go back a bit. This is asking again, what power do we put on 5 to get 5 to the 8th? Well, that would be 8. Same kind of thing here. What power do we put on 3 to get 3 to the x minus 2? Well, the power has to be x minus 2. This is a negative because the 9 is becoming one third. It's in the downstairs position, but it's also the square root of 9 becomes 3, so we have to call that a half. This is like those last couple. This one, again, this is a little bit weird. What power do we put on 16 to get a 2? We'll worry about the 1/2 later, but remember, it's the 4th root of 16 is 2. I'll put this over here. This is kind of helpful. The 4th root of 16 is 2. So that's like saying 16 to the 1/4 power is 2, but this isn't 2, this is 1/2. So it's the reciprocal of that, so I have to call that negative. Try that in the calculator just to verify that if you're not sure. This one, what power do I put on 2 to get 50? I actually don't have a lot of hope for this one. Well, let's see what we can kind of do. One of the tricks on this stuff like this, it kind of reminds me of that one we had at the very beginning with the 15. You can kind of bust this up into prime factors and see if it's any helpful. Like this is 2 times 5 squared. Is that helpful for anything? Well, this is, remember, if you have a thing here like that, you can add these together. This is log 2 plus log base 2 of 5 squared. This is nice. This comes out in the front like that, but really I'm kind of stuck when I get here. I can't really get any farther than that. I don't know if I've really evaluated this. I've rewritten it a new way. I don't know what log 2 5 is. It's not a really nice number. Same thing here. I think this one's even worse. Log 5 of prime factorization, that thing, it's 2 squared times 3. I don't think that's going to even get me really anywhere because it's base 5 and there's no 5 or exponents or in there or anything like that. I mean, I can try, but I mean, if you're really stuck, there's really nothing that's going to make that any better. So we're stuck right here. So evaluate is kind of a dead end there. It's just kind of like rewrite and kind of try and simplify, but find an equivalent expression, but I haven't really evaluated. Okay, great. Have a good fall break.